epsilon is known. So this boils down to two law. We went through this example that directly utilizes this formula. That's where we stopped in our last class. Okay. Then this this concept of Chebyshev inequality, sample mean, boils down to two laws of large number. Guys, those who downloaded previous version of my slide, please download it from the course, from the Canvas site, because last night I updated my slide. So here I included some graphical, some figures which were not present in the previous version. So here, because we are talking about some sample data, sample measurements, these two laws of large numbers, people get confused. So these days people use the term, you know that, right? LLM, large language model. So this LLM, this term, people use this term a lot these days. But LLM, it's very close to this term, and this term was born like many decades ago. LLM, laws of large numbers. So please don't get confused. This is large language model, and this is laws of large numbers. It's basically laws of physics, something like that. So laws of large numbers. So number of measurements affect the decision. That's the ultimate objective of these laws. That laws of a number of measurements, depending on how many number of measurements we take, that affect the decision, which makes sense. So here, do you recall that in our first chapter we went to relative frequency? Relative frequency in our first chapter, you also did one exam in computer assignment, where the relative frequency of event A, that number of times event A happened over the total number of trials. So this is relative frequency. When n goes to infinity, when number of trials goes to infinity, that relative frequency converges to probability of A. So that's where the probability comes from. So, but now after going through chapter 1 to chapter 5, we are going back to chapter 1, where we talked about the relative frequency, because that is the practical scenario, because it relies on the data that you collect. So here we are talking about number of data, raw data. So this raw data, depending on number of data that you get, gives two different laws of numbers. One is weak law of large number. The other one is SLM, strong law of large number. So weak law of large number says that you have finite number of measurements, and you can actually calculate the sample, not the entire population, sample. But when this number of measurement goes to infinity, this sample mean boils down to expectation, which is basically true that I mentioned in the beginning. So just to reiterate that you start with repeated samples, x1, x2, x up n, calculate the sample mean, and then when n becomes large, it becomes true mean. So I just illustrated this through a graphical row. Now this weak laws of large numbers, because we have here finite number of samples, we can make use of Chebyshev inequality. Here, utilizing Chebyshev inequality, weak law of large number is stated right here. So weak law of large number starts with the fact that all the random variables x1, x2, x sub n, these are IID. Previously we did not assume that it's IID, but when it comes to weak laws of large number, we assume that x1, x2, x sub n are IID. Okay, I want to reiterate, even though I did mention in our last class, IID means independent and identically distributed random variable. I'm just going to quickly, because this term is very important. I will be utilizing this again and again. So IID means independent and identically distributed. What does that mean? I know that it's IID, it's the acronym, independent and identically distributed. What does that mean? What does this mean? It means that if you have a first trial of a random experiment, and first trial will give you a random number x1, okay, and you represent it with the random variable x1, but this x1, it's, even though it's a random variable, but you do not know its distribution at all, but you do know this raw data. So this is basically raw data. And then you have x1, x2, and you get some raw data, and this raw data could be any data, so you do not know. You do know, but it can have, like when you have the second trial, the data that you see, when you see the data, when you take the measurement, that time you know. But it could follow any distribution. So x2, so dotted, x sub n, and it is xn. So let's have another random variable x sub j here. Okay? And here you have x sub j. What it means that because this is a random variable, this measurement could be random. So that's why this random variable will have an expectation, x sub 1, will have an expectation. And this random variable will have another expectation of x2, will have expectation. And I denoted with mu1, and I denoted with mu2. Okay? But these are unknown. These are unknown. mu1, mu2, we do not know. But we do know these measurements, but we do not know. So if we know the number of measurements, then probably like we can calculate the sample mean, but these are true mean. So here x sub j, expectation of x sub j is mu sub j. So these are true mean. And similarly, expectation of x sub n is mu sub n. So these are true mean. True mean. Okay. What IID means, guys? So these are, so far these are trivial. What IID means is this condition. IID means that expectation of x sub j, x sub 1 equals expectation of x sub 2. I will be directly utilizing this formula. Dotted equals expectation of x sub j equals dotted equals expectation of x sub n equals mu sub n equals mu, which means that all the true means of all the random variables is same, exactly the same. So this is what IID means practically, that all the random variables will have the same mean. Not only same mean, so it's basically mu1 equals mu2 equals dotted mu sub j dotted mu sub n equals mu. That's all what it means. That IID means that all random variables will have same mean. We do not know that mean. We may not know the mean, Like if we work with sample mean, that's okay, but true mean we do not know. And then this is one condition, that all the means are set for IID if the random variables are IID. And number two conditions, if the random variables are IID, then the variance of x1 equals variance of x2 equals dotted dotted equals variance of x sub j equals dotted dotted equals variance of x sub n equals variance of x equals sigma squared. So all variance of all random variables will be the same. So all random variables will have same mean and variance for the random variables to be independent and identically distributed, IID. So in short, you can write it like sigma 1 squared equals sigma 2 squared equals dotted dotted equals sigma j squared equals dotted dotted equals sigma n squared equals sigma squared. So that's all what is independent and identically distributed random variable means. So if we have x1, x2 dotted dotted x sub n be IID random variables. Now you should not have any confusion when I keep repeating IID random variables. With finite mean, which means that the mean of each random variable, which is denoted with mu, is finite. And finite variance, sigma squared equals variance of x. So for finite number of samples, we compute if sample mean. So this is sample mean. Sample mean. This sample mean equals 1 over n, summation I equals 1 to n xi. Then for every epsilon, so this is epsilon, it's called epsilon. For epsilon greater than 0, probability that the difference between sample mean and true mean less than some small number is going to be determined, is going to be lower bounded with this condition. That's what this Chebyshev inequality is about. So 1 minus sigma squared over n sigma squared. And therefore, this weak law of large numbers says that if we can compute sample mean like that, and then as we increase n, then probability that the sample mean, the difference between sample mean and true mean will be less than some small number is going to be 1. Okay? And this is what I explained using this slide. Okay. Please don't post. I think this computer died. All right, you know what? I'm going to use whiteboard. This computer died, and this touch screen doesn't work. You guys have my slide, so that's not a problem. You can use your cell phone, like those who do not have. Computer. So I have up to date slide. Now, I do not have marker. Does anybody have any marker? All right. So in slide number 216, I did mention that if y-axis is the sample mean and x-axis is the number of measurements. So number of measurements, if the number of measurement is 1, sample mean is going to be somewhere here. If the number of measurements is 2, sample mean, so 2 measurements, if they average, sample mean could be here. And if the number of measurements, let's say 3, sample mean could be here. So in that case, you see this sample mean is going to vary. And then as n goes to infinity, this sample mean is going to converge to expectation of x. Expectation of x, which is the true mean. Which is basically the true mean. So Wick law of large number says that the probability that the absolute value, it does not care about the sign, absolute value of the difference between sample mean and the true mean is going to be less than certain small number. This probability is going to be lower bounded by 1 minus sigma squared over n epsilon squared. Yeah. So this is the weak law of large number, and strong law of large number strong law of large number doesn't make the okay. Strong law of large number says that this is the next slide. You guys can see it if I write it. Okay. Strong law of large number says strong law of large number. Why do you need a strong law of large number? Weak law of large number, there is a problem in weak law of large number, because if we have certain number of measurements, it does not actually say what happens if you take additional measurements. It cannot give you formal behavior. It cannot explain formal behavior of strong law of large number. It cannot explain the behavior of the sample mean as a function of n. Okay, that's where the strong law of large number comes handy. Strong law of large number says that probability that limit n goes to infinity. Now you can actually write it as function of n. If n goes to infinity, so probability that as n goes to infinity, the sample mean becomes the true mean. This probability is going to be 1. So now it becomes a function of n. So for additional measurement, you can actually make this conclusion, and you would be able to see that as with probability 100%, the sequence of sample means eventually approaches to the true mean, which is trivial. Now let's move on to There is one example, that example I'm going to, it's very similar to the previous example. I'm going to give this example as part of your homework. So we are going to move on to central limit theorem, which is the most important topic of this chapter. Chapter 7, central limit theorem is the most important topic. Okay, as you see that, even each section, one topic is more important than the other topic because we are moving close to some practical scenario. Central limit theorem. So let me explain what this central limit theorem is about. There are some theory here. I have some block diagrams. Let me explain what it is. Okay. Why it is important? Central limit theorem and advanced studies of probability statistics, random processes starts with this central limit theorem. What is that? Started working now? No, it is not working. It is giving me some weird signal. Okay, central limit theorem. Guys, you open my slide. So let me explain a little bit about it. Central limit theorem. In this chapter, we said that we just know some raw measurements, raw data. We do not know the probability model of each random variable. Now, this random variable, guys, this random variable could be Gaussian random variable, this random variable could be Bernoulli random variable, this random variable could be binomial random variable, this random variable could be Pascal random variable, this random variable could be exponential random variable, any random variable. What central limit theorem says that doesn't matter what random variable it is, okay? When you add these random variables, as n goes to infinity, the summation of this random variable, something happens because something happened actually. So yes, scope is here, something happened. So with the system, electricity. So what happens, summation of random variables follows Gaussian distribution. That's all what the central limit theorem says. That doesn't matter x1, x2, x3, dotted, x sub n. These random variables would follow any random variable. When you sum them up, this summation becomes Gaussian random variable. That's why Gaussian random variable is very, very important. Gaussian random variable is super important. And I spent a lot of time talking about Gaussian random variable in chapter number 4. So Gaussian random variable, people will talk about some Kalman filters, okay, estimating signals, estimating, for navigation system, estimating position and velocity. So all these start with Gaussian random variable. Why? Is because of this central limit theorem. This central limit theorem, again, just to reiterate, central limit theorem says that does not matter what sort of random variable x1, x2, dotted, x sub n is, as n goes to infinity, when you add them up, this summation becomes a Gaussian limit theorem. That's all this central limit theorem says. So, okay. I explained to you the main idea. So the main idea here is that we have x1, x2, dotted, dotted, x sub n. The condition here, these are IID random variables. IID random variables, we are interested in the summation. Summation, which is x1, x2, dotted, dotted, x sub n. We are interested in this summation. And this summation, we do not know what sort of random variable this x1, x2, dotted, dotted, x sub n. This summation, Sn, is going to follow Gaussian distribution with mean n mu, and the variance is n sigma squared. What is mu? Mu is basically expectation of x1, expectation of x2, dotted, dotted, expectation of x, which is mu, and variance of x1, dotted, dotted, variance of x2, which is sigma squared. So, see the difference here. Again, we do not know what distribution these random variables follow. But when you add them up, this summation follows Gaussian distribution. So we do know what is Gaussian distribution. So Gaussian distribution with parameter mu and variance sigma n squared, you can actually know what is the distribution. So PDF of random variable Sn becomes 1 over square root over n sigma squared, and then 2 pi square root over 2 pi, and then e to the negative half Sn minus n mu over square, here n sigma square, and this is the PDF. So now you do know what is the distribution of the summation of n random variables because of the central limit theorem. So central limit theorem, again, I'm saying again and again, math you guys will understand. So because these are just simply addition, subtraction, or some terminology. But main idea, if you understand main idea, then it's a piece of cake. So if you have multiple random variables that follow IID properties, independent and identically distributed properties, and you do not know, you don't have to know the distribution of those random variables, then summation of those random variables follow Gaussian distribution. And what are the parameters? Mean and variance of that Gaussian distribution is n mu and n sigma square. There is another variation of central limit theorem. There is another variation of central limit theorem that you can normalize this random variable. So you can normalize this random variable. So normalization of this random variable, normalization, you can normalize using Zn, which is Sn minus n mu over sigma square root over n. So you can actually normalize this random variable. I have this in my slide. See, if you normalize this random variable, and this normalized random variable become the standard normal random variable. Standard normal random variable. You guys remember the standard normal random variable? So standard, if x is a standard Gaussian random variable or standard normal variable, so that has mean zero and variance. So this is a standard Gaussian. Standard Gaussian random variable. So in our case, using central limit theorem, it is the Zn. It is Zn that is going to follow the standard that is going to follow the standard Gaussian random variable. In our case, it is here. One more time, I'm going to rewrite it. This central limit theorem, the condition of the central limit theorem that all the variables that you take into account, these variables can be any random variable. Doesn't matter what random variable it is. Can be any random variable. But condition here is that these random variables follow IID distribution. If these random variables follow IID distribution, IID property, independent and identically distributed, you know the mean and variance of each random variable, like mean and variance, in case it is known or based on the measurements we see. But the condition here that all the means of each random variable, same mean, same variance. In that case, this summation becomes, you can guarantee, it is guaranteed this summation is going to be a Gaussian random variable. That's why people use this central limit theorem a lot, and that's why people use this Gaussian random variable a lot. And we spent significant amount of time in chapter number 4 talking about Gaussian random variable, what is the standard normal random variable, what is the standard cumulative distribution function, what is the standard complementary distribution function, Q function, and phi. Okay, we went through that. So I actually explained in my slide, which is slide number 220. Here to the right, I have a nice block diagram. So I started with samples, and then you calculate sum or mean. Okay. So once you normalize the random variable, this normalized random variable becomes a Gaussian random variable with mean 0 and variance 1. Now, I did talk about the normalization of the sum of random variable. You can actually have the sample mean as well. So there is another equation, sample mean. It is actually coming from Sn. Sample mean Mn is basically Sn over n. Sample mean is basically Sn over n. And as n goes to infinity, if we have x1, x2, dotted, xm, these are IID, then this sample mean is going to be, this sample mean is going to follow Gaussian distribution with, for sum of random variable, mean becomes n mu, because sample mean is basically Sn divided by n, so that's why it's a sample mean will have a parameter mu, because n mu over n is going to be simply mu. Okay, mu, and the variance is going to be sigma squared over n. Variance is going to be sigma squared over n. And that's exactly what I have in my slide. Yeah, so if you look at the next slide, so I call it CLT interpretation, okay? How do you interpret that as n goes to infinity, Sn becomes a normal Gaussian distribution with parameter n mu and sigma squared, and sample mean becomes a normal distribution or Gaussian distribution with parameter mu and sigma squared over n. And another version I showed you, that is Zn in terms of standard normal Gaussian distribution, which is Zn follows a standard Gaussian distribution with parameter 0 and 1. Now we can directly use this central limit theorem to find the probability problem, to solve some probability problem. Do you guys see on slide number 22, I have 4 steps how to apply the central limit theorem. You see that? In step 1, 2, 3, 4. Okay? So I am going to directly use these 4 steps that directly uses these 4 steps, use central limit theorem to find the probability. Okay, the first step is you start with the problem and try to find, somehow you try to represent the random variables as the sum of random variables, okay? And you make sure that the random variables are IID. If you are not sure about random variables being IID, you simply cannot apply. You simply cannot apply central limit theorem. So the first condition here is that random variables have to be IID, independent and identically distributed. And then you compute the mean and variance. Step 2, you compute the mean and variance. So using the formula I have, like for mean of sum of random variables, it is n mu, and variance of sum of random variables is n sigma squared. And then you normalize. Normalize the sum and use central limit theorem. So you normalize the sum Zn equals Sn minus n mu over sigma square root over n. And as n goes to infinity, and now this Gn becomes a standard normal random variable with parameter 0 and variance 1. Now step 4, now we can use this central limit theorem result to compute the probability. So probability that a random variable takes value between a and b is given by the formula that I have right here, which is phi. It is probability that Sn takes value between a less than or equals Sn less than or equals b equals phi parameter your Sn minus n mu over square root over n sigma square root over n Now, because we have the upper limit here b, so you have b here. So instead of Sn, you write b minus, and you have phi a minus n mu over sigma square root over n. So this is basically the formula. What is phi, guys? Do you remember what is phi? Phi is the standard. Phi is the standard cumulative distribution function, CDF function, standard cumulative distribution function of Gaussian random variable. And the relation between phi and q, so phi of x equals 1 minus q of x. Do you remember q table, guys? Okay, so make sure in the exam you bring the q table. You bring the q table. So this is the relation between phi and q. Phi is the standard cumulative distribution function of a Gaussian random variable, and q is the standard complementary cumulative distribution function of a random variable, of a Gaussian random variable with parameter mean 0 and variance 1. So we have one example 7.11. Yeah, example 7.11. Let's go through this example. Suppose that orders at a restaurant are IID random variables with mean mu equals 8 and standard deviation sigma equals 2, estimate the probability that the first 100 customers spent a total of more than $840, and estimate the probability that the first 100 customers spent a total between $780 and $820. It's very similar to one of the chapter 4 problems we went through in class. So we did make use of the Q table to determine the probability. Here it's very similar to that, except that here we are going to use a central limit theorem.
There's a break time. You guys think I could run to the meal hall and back in time?
Okay, guys,
Not break time.
let's solve this solution. Suppose that orders at a restaurant are IIT, any other pizza restaurant or whatever, any restaurant, IIT random variables with mean $8 and standard deviation $2. What it means that customers are ordering and owner sees that based on experience, whatever, like a customer, on an average, one customer orders worth of $8, okay? And some customer orders $9, some customers $6, $7, whatever. On average, it's $8. And the standard deviation between orders, among orders, is sigma equals $2. So what the first problem says that estimate the probability that the first 100 customers spent a total more than $840. So now what we are going to do, number one solution, step 1. Actually here, x1, x2 orders x1, x2 dotted. How many orders, guys? X100. So n equals 100. Follow IID property. Okay? These random variables follow IID property. Now, the main objective here is that we have Sn, which is S100, which is x1 plus x2 plus dotted. First 100 customers will have a total O is S100. So the objective here, what is the probability that S100 is greater than $840? What is this probability? That's all the problem is. So I want to determine what is the probability that the first 100 customer will spend total or more than $840. So now see how I apply central limit theorem. Step 1. Step 1, we already have Sn. Sn equals x1 plus, actually, you write it down. We already have S100 equals x1 plus x2 plus dotted plus x100. So we already have this. Step 2. Step 2, compute the mean and variance. So we already know what is mean. Mean E of x1 equals E of x2 equals dotted equals E of x100. This mean, owner knows that, okay, on average each customer spends $8. So this mean is $8. So mu equals 8. And then variance of x1 equals variance of x2 equals dotted equals variance of x100. Equals sigma squared. So which is basically 2 squared, which is 4. So we know this variance equals 4. Okay. Now you compute mean and variance of S. So expectation of S100 is n mu, which is n equals 100 and mu equals 8 equals 800. So the summation has a mean of 800 and the variance of this summation, so variance of S100 is n sigma squared, which is 100 times sigma equals 2, sigma squared equals 4, so this 4 equals 400. So now we know the mean and variance of the sum of the orders, total order. So once we know the mean and variance, we use central limit theorem for n equals 100. Step 3, you standardize and use central limit theorem. So standardization is Z equals S100 minus n mu over sigma square root over n. You substitute all the values. S100, you do not know what is S100. All what we know the mean and variance of S100, but we do not know what is S100. But we do know n, which is 100 times mean mean of each order is 8 over, this is 2 square root over 100. So this will give you Z equals S100 minus 800 over 20. Using central limit theorem, this normalization using CLT, central limit theorem. Using central limit theorem, Z becomes a Gaussian random variable with parameter 0 and 1. So using central limit theorem, this Z becomes a Gaussian random variable. Previously, we had no idea what distribution, this summation of 100 orders will look like. Now, because of central limit theorem, we say that, okay, we have 100 orders. Okay, let's use central limit theorem. So using central limit theorem, we do know that this Z, this normalized random variable, will follow a Gaussian distribution with parameter 0 and 1. And Sn and S100 is going to follow a Gaussian distribution with parameter n mu, which is n 100 times mu 8, which is 800, and what is the variance, guys? The variance is 400. Okay, so we are able to write this Z and S100. We are guarantee these two variables are Gaussian random variables just because of the central limit theorem. Okay, so now it is time to compute the probability. Step 4. Step 4, we compute the probability. So this probability that S100 is greater than $840. So what we do, we are going to normalize this S100. So we say probability that we subtract S100, we subtract 800 n mu from S100 over 20 greater than, we have 840 minus 800 over 20. We subtracted 800, we divided by 20, both sides of the inequality, just to make sure that we write it as a standard normal random variable, which is Z in our case. Z greater than, it is 840 minus 800 is 40 over 20, is going to be 2. Okay, so the definition of the standard random variable x less than x is basically your Q2. And this Q2, from the Q table, you see that it is 0.228. And that is one answer. Probability that S100 greater than 840 is 280. Okay, so this is one answer. We'll go through the second. Part of the example in the second half. So, guys, you take 5 minutes.